Welcome and thank you for joining us for the OAR 2021 Outstanding Scientific Paper Recognition event. My name is Camille Henry, and I am honored to serve as the OAR Awards Program Manager. Before we begin, I would like to notify everyone that this event is being recorded, and the closed captioning link can be found in the chat box. Today, we will recognize employees for their significant contributions to our organization and NOAA as a whole. The Outstanding Scientific Paper Award recognizes the science that is published through rigorous peer review processes. This year, the OAR Awards program received a total of 32 nominations for the Outstanding Scientific Paper. And today we will recognize the 3 winning papers, as well as hear from the primary authors in a form of a lightning talk. There will also be time at the end of the event for Q&A. It is now my pleasure to welcome the OAR Assistant Administrator, Craig McLean, for opening remarks. And following, we will hear from the OAR Deputy Assistant Administrator of Science, Gary Matlock. Craig, I turn the presentation over to you.
Thank you very much, Camille, and thank you to the library team, in particular Katie and others who have helped to work to make this come. And I want to welcome and thank Mr. Wilson for his American Sign Language interpretation. It's very important that we remind each other how we are an inclusive organization. When I look at the opportunity to be recognizing or contributing to the recognition of our outstanding scientific papers, I can step back and think, for the many years that I've been here, what a prestigious place these awards have on the walls of previous recipients. This means a lot to you, and it means a lot to us. I am very proud to see who the individuals are who are being recognized, the many co-authors that will be recognized in this year's conveyance of the awards. And if I also take note of the calendar day, we're within a day of 2 years of being in the COVID lockdown or the COVID seclusion. And over those 2 years, as these papers will reflect, we've not slowed the pace or the productivity of our science. It would be naive of me to think that there was no impact. Of course there was. But when I see the science that has resulted and is recognized in the production of these papers that have been awarded and the remaining papers that were part of the original nominated submissions, it makes me very proud to realize that here we are, a truly outstanding science organization in an agency that brings important information to the public on a daily basis. So we truly have recognized here the finest science through these outstanding scientific papers. You may remember that we start with the notion of quality, relevance, and performance when we review a scientific program or laboratory. And that quality, that relevance, and the performance of the science is clearly reflected in the papers that were chosen this year and every year. But you also might recall when I first got here, I asked you to focus on the preeminence of our science, which these papers represent, the partnership, which as you look at the work and the impact of it is well represented, but also the results. We are generating results through our science that's usable by the public every day, and these papers remind us of that. So as we move on to make the recognitions, I just want to take a moment to thank the people who, Camille and your colleagues who are involved in the OAR Awards program, our awards board, the Employee Services Division of our headquarters, and our communications office for helping us to set up this ceremony. Normally, we would be in the auditorium. We would have the grace of having invited the family members of the winners, or the awardees, and we unfortunately just do the best we can until we can all be back in the same place together. But a number of other people were involved in making sure that we conducted the review of these papers. So I want to thank the portfolio advisors, the many reviewers who took to task the opportunity and responsibility to review and rank the papers, the people from our NOAA Library Services who are hosting here, but in particular, I want to thank the nominators, because without nominators, there would be no opportunity to recognize awardees. I want to thank also the authors of the many papers, the 32 papers, times many authors of each that have put their best work forward here. And you each continue to make NOAA and OAR the preeminent science organization that we are. So let's now move on towards the actual conveyance of the awards. And I'd like to now ask Gary Matlock, our Deputy Assistant Administrator for Science, to take the floor and commence with the awards. Gary, thank you very much.
Thank you, Craig, and welcome back from Hawaii. It's great to see you back on the stage here to participate in today's ceremony. I thought I would add a little bit to Craig's comments at the outset to answer a bit the question, why do we care about the scientific papers that get produced from within OAR using both the talents of the NOAA employees and the colleagues with whom they work? And the answer rests in the fact that these papers reflect the output, the products that NOAA produces in the scientific arena, which forms the basis for decisions that get made in NOAA and beyond. These papers also reflect the reality that they have been reviewed by peer scientists and have concluded that they are of sufficient quality to be published in the scientific literature. This is the process that we use in order to make sure that the science we are producing is worthy of being used in decisions that come thereafter. So with that very brief introduction, let me get to the business of awarding the papers, excuse me, of awarding the authors of the papers for the 3 papers that have been selected to receive awards, one in the climate paper category, one in weather, and one in oceans and Great Lakes. The climate paper category is reflected, the paper to be awarded in the climate paper category is for research entitled An Unexpected and Persistent Increase in Global Emissions of Ozone Depleting CFC 11. This paper reflects the first substantial violation of the Montreal Protocol on substances that deplete the ozone layer. The paper's findings are directly relevant to NOAA's mission as they involve understanding the unexpected atmospheric composition changes that are relevant to climate, given that CFC 11 and stratospheric ozone are greenhouse gases. The funding is highly relevant to the effort to be able to predict future levels of both CFC 11 and stratospheric ozone. The paper was nominated by Dr. Wayne Higgins, the director of the Climate Program Office, and the author today that will be presenting is the first listed author, Dr. Stephen Monska. In addition to Steve, there are several co-authors that should be recognized as well as Steve for their participation in the publication of the research in which they participated that led to this paper being published. They include Robert Portman, John Daniel, Bradley Hall, James Elkins, Jeff Dutton, Eric Ray, Carolina Ciso, J. David Nance, Matt Rigby, Lei Hugh, Fred Moore, Ben Miller, Deborah Mondial, Ping Fei Yu, Lambert Coupertz, and Alistair Manning. So with that introduction, Steve, the floor is yours.
Well, thanks so much, Gary. I really appreciate it for that introduction. And also to Gary and to Wayne for recognizing the work that we've put forth here, and also to Camille and other organizers of this event. I'm extremely pleased and honored to accept this recognition on behalf of the co-authors of paper who were extremely essential to its success. So as was mentioned, the paper was an outcome of our ongoing efforts at GML to monitor the chemical composition of the atmosphere Specifically, we were monitoring changes in ozone-depleting chemicals and their substitutes. The effort is central to the broader international effort to guide recovery of stratospheric ozone, that layer that protects humans and all other living things from the sun's harmful UV radiation. You know, it's easy to forget that life on Earth wouldn't exist as we know it today without the ozone layer. And in the 1980s, it was discovered that this layer was disappearing because of society's use of certain chemicals like CFCs that contain chlorine and bromine. And the international community organized a response then, agreed to and ratified an international protocol. And that protocol ultimately phased out the production of things, chemicals like CFCs that society used. And that body continues to meet even today, twice a year, to assess the effectiveness of existing controls to see if further action is required in order to save the ozone layer. It was shortly after that the US Clean Air Act was amended to mandate that NOAA and NASA would regularly report to Congress on the abundance of these gases to know when the ozone layer might become healed. And that's why day in and day out, you'll find instruments chugging away at GML with a number of those co-authors listed on the paper, measuring air samples, tracking changes in concentrations of CFCs and other ozone-depleting gases and their substitutes. And fortunately, not only just making the measurements, but also giving scientists the room to assess and understand the underlying causes for the changes being observed. So around 2014, I was overlooking results for CFC11, the second most abundant ozone-depleting substance, whose production was reportedly phased out globally in 2010. Its concentration had been declining fairly steadily since the 1990s, and that decline had been slowly accelerating until 2014. That's when it wasn't. The CFC11 concentration decline was slowing down. And the most obvious conclusion was that emissions, maybe use, maybe production of this chemical was back on the rise, even after the phase out of production. I was dumbstruck, frankly. The most surprising thing I've seen in my 30-year-plus career, a 30-plus year career, the implications were hard to fathom. The Montreal Protocol has been repeatedly held up as a shining example, the most successful international agreement ever. And yet here before me possibly was evidence suggesting otherwise, that someone somewhere was violating the Montreal Protocol. So in the next few years, with the help of a number of highly capable colleagues listed as co-authors, we explored alternative possibilities other than the most striking one, that the Montreal Protocol was being ignored and production of a banned substance had been restarted in large quantities. So there were three possible alternative explanations that we needed to investigate. First one, the obvious one, that the measurements were just wrong. Measuring these chemicals in the atmosphere is difficult, painstaking work, and the concentrations are extremely low levels. And we were looking at very small changes that had quite large implications. So we had to revisit the measurements. Second issue could have been that fundamental processes in the atmosphere were changing or becoming more variable and affecting CFC's rate of decline in the atmosphere, independent of emissions. And the final possibility was that emissions were increasing, but not from illegal production, but from instead as a result of increased leakage of the CFC11 from existing reservoirs, from production that was before this phase out or ban in production. So to look at the measurements, we went back to the lab to double, triple, quadruple check things with the help of folks like Jeff Dutton, Carolina Ciso, Brad Hall, to recheck and be sure that what we were seeing was a real signal in the atmosphere, not something that was a result of a problem here or there in these difficult measurements. And it was during this time that the redundancies in our measurement systems at GML and that comprehensiveness of that system proved their worth many times over. Ultimately, it was clear that all of our systems were pointing to the same conclusion, that CFC11 wasn't declining as it had been. Similarly, there were a number of hints in addition in the measurements because we make those measurements at many different sites. The distribution of the chemical also changed concurrently, such that there was more now being observed in the southern hemisphere than in the northern hemisphere than the south. Another hint came from looking very closely at our measurements at the Mauna Loa Observatory in the middle of the Pacific Ocean. Repeated minuscule increases in the CFC11 concentration began to be observed around 2013 that hadn't been seen in earlier years, and they coincided with enhancements of other chemicals known to be emitted in Asia. We backtracked the source of those air samples, and they seemed to point to Eastern Asia, suggesting that perhaps emissions had increased from those regions. And just to step back just briefly and make the point that this outcome was made possible through continuous efforts to improve our chemical analysis instrumentation over time. And without these improvements, like using the instruments that were maybe present 10 to 20 years ago, this signal, which would have been much harder to detect and diagnose, and ultimately it would have taken quite a bit longer to provide the actionable information that ultimately we were able to provide. So that we had fairly solid evidence for an emission increase, but we needed to understand the extent to which the changes were related to atmospheric transport or mixing processes. And fortunately, we had expertise that we could draw on there to address that issue within GML and CSL, particularly Eric Ray, John Daniel, Pengfei Yu, and Bob Portman were essential. And we met regularly to banter about ideas, possibilities, model runs, and calculations to redo many, many times over and over again. And it appeared that in the end, that atmospheric process could play a role. We're playing some role, but ultimately we couldn't avoid the conclusion that emissions indeed were increasing. And the outcome of this particular aspect of the work is that the long-term outcome is that we are now building tools to better account for variations in atmospheric process, to better use our atmospheric results, those atmospheric measurements that we're making, so that we can more directly and in a more timely fashion infer changes in human behavior or emissions separate from these other factors, to provide more ready and more relevant feedback to policymakers and scientists about emissions changing. So point 3, emissions were increasing, but ultimately was it a non-issue? Was there no new activity, no violation of the Montreal Protocol, but just an increase in emissions from older materials degrading over time? This also took some time to assess objectively, but we availed ourselves of help from industry experts such as Lambert Kuipers, who thought it was possible, but not likely. And upon further looking into this, it determined that it indeed was probably not the cause for what we were happening, but we were actually looking at renewed production. So in May of 2018, we published this paper announcing the discovery of the first substantial apparent violation of the protocol. In the words of a colleague associated or familiar with the work, he said it shook the Montreal Protocol to its foundation. We shared the results with other agencies, Chinese scientists and officials, and at the meetings of the party of the Montreal Protocol to assist their effort at better understanding the issue, its causes, and its potential resolution. Meetings were held, panels convened, special reports were requested and delivered by the different advisory committees to the Montreal Protocol. Loopholes in the Montreal Protocol were discussed and plans were made to address them. And most attention was directed towards China. And to their credit, they announced programs to more closely investigate chemical production throughout their country. And by 2019, in a follow-up study, in fact, Eastern China was identified through atmospheric measurements once again in Asia as being responsible for most of the emission increase. So another significant outcome is that the parties of the protocol are now engaged in an effort to fill the gaps in the global observing network that became strikingly apparent throughout the episode. Only a portion of the global emission increase was attributable to a specific region, which made resolving the issue much more difficult and uncertain. But now fast forward to 2021. Fortunately, we were able to continue making additional measurements, and by accounting for natural atmospheric changes, we published a follow-up study, also appearing in Nature, in which we document a dramatic decline in the global emissions of CFC11 after we published our paper after 2018. And it appears that global emission and the atmospheric decline of CFC11 are now close to being back on track. I'd just like to close by saying that how much this whole story aligns with NOAA's mission that's dedicated to developing and improving measurement systems and encouraging advances in scientific process that all enabled the atmospheric changes to be detected and also understood. And furthermore, our long-standing engagement with the international communities who have come to see NOAA as a trusted and reliable source of information who then pushed others for action. And in the end, it appears like the CFC-11 bullet was dodged this time, paving the way for ozone layer recovery to continue with only a small delay. So thanks again very much for this opportunity and for this recognition. Very much appreciated.
Steve, thank you very much for the summary of the science and also the impact of the science that has had in trying to make the conditions in which we live better. I appreciate very much you taking the time being with us, and congratulations again to you and all of your co-authors who participated in the paper. If folks will allow me as well a moment, NOAA has, and OAR in particular has, a very significant investment and focus and effort on observing systems in the environment, atmospherically, on land, in the water. And we have in OAR as an objective in our strategic plan, the notion of detecting changes in the environment. It is the long-term data collections that exist at the Global Monitoring Laboratory and around other parts of NOAA that have as their foundation the scientific hypothesis that there is no change in the atmosphere. The null hypothesis then is allowed to be examined as a result of the collection of these long-term data through time, hopefully not interrupted, or if interrupted, for only a short time. The benefit and the use, however, of those data go far beyond the ability to detect changes, as has been indicated by Steve and his co-authors in this paper. So it's with great delight that I see the expression of the benefits of long-term observations captured in this particular paper. Thank you again, Steve. Thank you again to all your co-authors. Our next paper is the winner of the Oceans and Great Lakes, and the paper is entitled The Oceanic Sink for Anthropogenic Carbon Dioxide from 1994 to 2007. It summarizes what is known about the inventory of anthropogenic carbon during this period and sets the stage for determining how the carbon system in the oceans will evolve in the future. The paper is the basis for both national and international assessments, such as the IPCC, the Global Carbon Project, and the annual State of the Climate Report. The paper was nominated by Dr. Michelle McClure, Director of the Pacific Marine Environmental Laboratory, and the presentation will be given by, excuse me, by the first listed author, Dr. Richard Feely. Co-authors for the paper, on the paper include Rick Wanenkoff, Alex Kozer, Brendan Carter, Nicholas Gruber, Dominic Clement, Stephen Van Heuven, Mario Hopema, Masao Ishii, Robert M. Key, Siv Lovset, Ari Olson, Claire Lomonaco, Jeremy Mathis, Akihiko Murata, Fiz Perez, Chris Sabine, and Tosti Tanua. With that introduction, Dick, I'll turn it over to you to make the presentation.
Thank you very much, Gary. And I want to thank OAR for recognizing these scientific papers. I think this is a tremendous award, and we are extremely humbled by the opportunity to receive this award. I want to give a little bit of background of the research and motivation behind the paper, and then I will talk a little bit more about the paper itself. If I could have the slides, please. over the last 40 years, we have been observing and modeling the year-to-year changes in the uptake and release of carbon dioxide from fossil fuel burning. And we have been studying the changes that are occurring in the atmosphere, in the land, and the ocean. And we have been using both models and observations to assess these changes, and these are done by the Global Carbon Project. Our major scientific question is, what is the partitioning of the CO2 that's released from humankind into the atmosphere between the land, the air, and the oceans? And secondly, what are the controls of the decadal variations in the ocean uptake and transport throughout the global ocean? And thirdly, and most importantly, is the ocean uptake of anthropogenic carbon dioxide keeping pace with the atmosphere, or does it respond to climate change and some nonlinear variation? Next slide, please. So what we have done over the years is to develop some very good, elegant models of the changes that would occur in the atmosphere and ocean and land biosphere as a function of release in CO2 in the atmosphere. And the concept was very simple in the beginning, that the current generation of models simulated an ocean uptake that was relatively constant and directly related to the atmospheric increase. And this slide shows that. And it shows the initial work of Chris Sabine in 2004, when we integrated all the data sets. And what we saw was that their constant uptake model differed between the different models quite a bit. So the inventory of anthropogenic carbon in the oceans provide us with a ground truthing of the models themselves, and indicated that the fraction of uptake by the oceans is anywhere from 14 to 31%. Next slide, please. And at that time, the models that were being considered and being used were models that had a constant uptake fraction, and they indicated quite large variability between each of the models themselves in comparison with the global mean from the observations. Next slide, please. So what we did, in working with David Legler and Kathy Tedesco of the Global Ocean Observing and Monitoring Division, we developed an international effort of repeat hydrographic cruises known as GOSHIP, in which we're able to observe the chemical changes on a decadal basis throughout the global oceans, starting in the late 1980s to the present. And we were to support that with surface measurements on moorings and surface ships, and utilize the combined data sets of the observations in surface waters and the ocean interior to get a sense for the decadal changes of carbon uptake within the oceans and in the ocean interior, and use that information to compare to the models for the uptake of carbon dioxide. Next slide, please. And so together with our international partners, we developed in the international SOCAT, the Surface Ocean Network, which now has 10 million measurements, and the GLODAP, which is the Ocean Interior Network, which has 724 cruises and over 500,000 observations. The United States provides about half those measurements by a collaborative effort between NOAA and the National Science Foundation, and our colleagues throughout the world provide the other half of those measurements. Next slide, please. Now, the paper that is being awarded today was led by Nikki Gruber from ETH, and Nikki is a colleague of ours. He got his postdoc at Princeton University, working with us from the beginning. Not only did he participate in the synthesis of all this data with us, but he actually helped design all the methods that we used to do the synthesis. And some of the initial work on the methods themselves were designed and developed by Nikki and his team. Within NOAA, we have Brendan Carter, myself, Robert Key, Alex Cozier, Jeremy Mathis, Chris Sabine, and Rick Weinikoff, all participating. There are 14 countries involved in this effort and 18 scientists that provided the data sets, that integrated the data sets, and conducted the synthesis analysis in a completely collaborative manner. And this paper here is the second set of data set. The original data set was developed by Chris Sabine. This is the second set, and we're now actually this year into our third analysis, the third decade analysis of the data sets. Next slide, please. And here's the original work by Chris Sabine, published in 2004. And you can see that we were able to use surface to bottom measurements to determine the inventory of anthropogenic carbon during the decade of the 1990s. And next slide, please. And this is the data set now for the second round, developed by this paper from 1994 to 2007. And this shows the changes that have taken place since 1994, with strong accumulation in the Southern Ocean thermocline in all three basins, and moderate increases also in the deep North Atlantic. Next slide, please. And so when we make these comparisons between the two decades, the 1994 on the bottom and the 1994 to 2007 on the top, we can see the changes that have taken place, and we can see the striking increases in anthropogenic CO2 through the Southern Ocean mid-latitude regions, where it is building up in the thermocline, being derived from the high latitudes and being transported and built up within the thermocline and accumulating there, also accumulating in the North Atlantic. Next slide, please. And so when we look at the changes between the 1990s and the 2000s, we can see significant changes that have taken place, suggesting that the oceans behave in response to climate change. And as climate change changes, the ocean responds quickly. In the 1990s, we found that there was a very small uptake taking due to the changes that was occurring in the surface layers, the air-sea exchange, that had a small uptake. But in the deeper waters, there was mostly outgassing at the time, and so that there was a net effect of a very small outgassing in the 1990s. In the 2000s, we found a significant change, that the air-sea interactions responded to the changes in the temperatures. There were very strong temperature anomalies in the 2000s, which caused a stronger uptake in surface waters, and also a strong uptake in the subsurface waters. And these uptake in the subsurface waters, particularly in the Pacific and Indian Ocean sector, caused a very dramatic decadal changes that were occurring there. And this is due to the influence of these changing wind forcing and the changing surface temperatures that cause this uptake. So a net effect is a much stronger uptake of carbon dioxide due to the changing climate over this decade. Next slide, please. Next slide. We can see the changes that took place in this accounting for 2019 up to 1994, and from 1994 to 2007, we saw a total uptake of about 34 petagrams of carbon in that time frame. And there was some release of CO2 back to the atmosphere, so that the net uptake was about 29 petagrams of carbon during that time frame. And that change in uptake was due to response of the oceans to the changing climate that is taking place. And that uptake is primarily in the Southern Ocean region, where we have strong uptake of carbon dioxide, movement towards the to the north, and then accumulating in the deeper waters of the subtropical regions in the southern hemisphere. Next slide, please. Now, a major effort has been done to make a comparison between what we've learned from the models in comparison to what we've learned from the observations. And what we see here in this slide over the long record is that there is general good agreement between the models and the observations up through 2000. And then from 2000 on, we began to see that the ocean uptake from the observations is beginning to be a little different from the model outputs, and that disparity that we're seeing is right at the edge of the uncertainties of the measurements. So by utilizing the ocean data from the repeat hydrographic cruises, we began to be able to provide an additional data point for the uptake of that carbon, which has much lower uncertainty than we get from the surface measurements themselves. This is the red dot in the center here, showing the uptake based on the research presented in this work. And you can see that the global accumulation of carbon from the interior ocean data set represented here agrees quite well with the oceanic measurements for the region, indicating uptake of carbon dioxide that is commensurate with the increase in CO2 from the atmosphere at a constant rate of about 25% of the total uptake. The amount of uptake represents about a $500 million a year in terms of uptake of carbon, in terms of carbon credits. So we are seeing a very important role of the ocean and taking up that carbon dioxide from the atmosphere. And the question is now is whether the oceans will continue to have that uptake in response to climate change. Next slide. So our conclusions is that so far the oceans is keeping pace with the atmosphere, and that the uptake of excess carbon is continue to come along at the same rate of increase as it has in the past. And some of the most recent measurements presented at Ocean Sciences meeting this past year has shown exactly that. And that uptake is about 20% of the total amounts released. And that the storage of that carbon dioxide in the ocean varies from one decade to the other, depending on the changing conditions due to climate change. And that means that the ocean response will have a high degree of decadal variability. And that means that the ocean response to climate is significantly important, that we maintain and understand how the oceans are changing and that uptake of carbon dioxide. And it's only through the combined efforts of the modeling effort and the observational efforts that are directed by NOAA and the National Science Foundation and our colleagues throughout the world that we've been able to document these changes from surface to bottom. I will stop there and take any questions.
Thank you, Dick. I think we're holding the questions until the end of the three presentations. So if we can then move on to the third presentation before there are any questions. Again, the power of long-term observations becomes so evident, this time in the oceans, just as it was in the atmosphere. So thank you very much, Dick. Congratulations to you and all of the co-authors on this really important science that you've published. Excuse me. Our last paper is the winner of the weather category. The research paper is titled Improvements to Lake Effect Snow Forecasts Using a One-Way Air-Lake Model Coupling Approach. It details the first ever short-term weather forecast coupling between an operational weather model and an operational hydrodynamic lake model. The paper is the first to detail how to couple operational weather models and operational hydrodynamic and lake ice models, and has set the stage for implementation into NOAA operations. This operational setup will be the new paradigm for NOAA air-lake coupling for the foreseeable future. The paper was nominated by Ms. Deborah Lee, Director of the Great Lakes Environmental Research Laboratory, and the primary author that will be presenting today is Ayumi Fujisaka Nome. Hopefully I got the name close to right. In addition to Ayumi, additional authors include Greg Mann, Eric Anderson, Philip Chu, Curtis Alexander, Stan Benjamin, Eric James, Tatiana Smirnova, Lindsay Fitzpatrick, and David Wright. With that brief introduction, Ayumi, I'll turn the presentation over to you.
Thank you so much, Gary. You got my name pronunciation correct. Thank you for that too. Thank you so much for the committee for organizing this event. Hello, everyone. On behalf of the co-authors, I am extremely honored to be here for the OAR Outstanding Paper Award. And it is my pleasure to introduce the findings of our paper at this venue. Lake effect snow is a hazardous winter weather that impacts coastal communities in many different ways. It can result in low visibility, stranded traffic, power outages, utility damage, and in some occasions, fatalities can happen. Lake effect snow occurs when dry air mass passes over a large water surface and picks up moisture in winter, resulting in downwind snowfall. Lake effect snow is most well documented in the Great Lakes region, but it occurs at many different locations where a cold air mass migrates over a relatively warm, large water surface, such as the Sea of Japan, Great Salt Lake, and the Baltic Sea. Accurate prediction of lake effect snow is challenging, especially in terms of where, when, and how much snow we will get over the next couple of days. Convections associated with lake effect snow occur at a few kilometers, which can barely be captured by regular numerical weather forecast models that do not resolve convections. In addition, lake surface conditions change rapidly over the duration of a lake effect snow event. Water surface cools down as the cold air absorbs sensible and latent heat. In some cases, ice cover develops as a result of cooling. These significantly impact behavior of lake effect snow, but in the conventional numerical weather forecast models, lake surface conditions remain the same over the forecast horizon, and therefore these rapid changes are not represented in these models. Coupling of weather and lake models is a promising way to improve lake effect snow precipitation prediction, as it allows the model to represent rapid changes in lake surface conditions. However, there will be a huge computational cost, especially for high-resolution models that capture convections. In addition, for large water bodies like the Great Lakes, a three-dimensional hydrodynamic and ice model is typically used to predict physical processes because of ocean-like features in these large water bodies. Because of the huge computational expense, full coupling between the weather and lake models are not practical in the operational environment at NOAA. In this paper, we demonstrated a novel model coupling approach called loose coupling or one-way coupling. In this loose coupling technique, the data of model predictions are exchanged between the hydrodynamic ice model based on the finite volume community ocean model coupled with the unstructured grid version of Los Alamos sea ice model, or FBCOM sea ice, and the experimental version of high-resolution rapid refresh model, which is the NOAA's weather forecast model based on weather research and forecasting model, or WRF. These data exchanges occur iteratively and allow representation of rapid changes of the lake surface conditions such as water surface cooling and ice formation. Yet, this loose coupling technique requires little increase in computational expense, and therefore this technique is practical for applications in the operational environment at NOAA. In this paper, we not only demonstrated the implementation of this loose coupling technique, but also demonstrated significant improvement in representation of rapid changes of water surface temperature and ice cover, as well as the prediction of snow water equivalent during 3 lake effect snow event that occurred over the Great Lakes region. This work builds on recent development of the Great Lakes Operational Forecast System, or GROF, which is currently transitioned to operations at the National Ocean Service Center for Operational Oceanographic Products and Services, or COOPS, as well as the latest operational NOAA's high-resolution rapid refresh weather forecast model. I'd like to highlight that this work has been a collaboration across NOAA's line offices between the 2 OAR labs, namely Great Lakes Environmental Research Lab and Global Systems Laboratory, National Weather Service Weather Forecast Office in Detroit, as well as 2 cooperative institutes, namely Cooperative Institute for Great Lakes Research at University of Michigan and Cooperative Institute for Research in Environmental Sciences at the University of Colorado Boulder. Finally, and most importantly, I'd like to underscore that all co-authors played really strong roles in making this work possible. Greg Mann from National Weather Service, Eric Anderson and Philip Chu from Great Lakes Environmental Research Lab, Lindsay Fitzpatrick from Cooperative Institute for Great Lakes Research, Stan Benjamin and Curtis Alexander from Global Systems Laboratory, Eric James and Tanya Simanova from Cooperative Institute for Research in Environmental Science, and David Wright from the University of Michigan, Ann Arbor. Myself is just an ice and hydrodynamic modeler, and this work could not happen without the expertise that all co-authors and beyond brought in. So I'd like to express my thank you to all the authors. I'd also like to express my gratitude to the Great Lakes Environmental Research Lab Director, Ms. Debbie Lee, and also the nomination committee for nominating our paper to this prestigious award. With that, I'd like to conclude my speech. Thank you again for having us here for this important award.
Ayumi, thank you very much for a really informative presentation. Congratulations to you and to all of your co-authors for receiving the award from OAR. You can also tell there's sort of a consistent theme across all of these papers, and Ayumi did a terrific job in recognizing the power of collaboration. The collaborations reflected in these papers go beyond a single OAR lab or a single OAR scientist. They extend across the line offices in NOAA, they extend within OAR, and they extend outside, both nationally and internationally. And as a result of those collaborations and the scientific thinking that people provide in conducting the research and publishing the papers, OAR, NOAA, and society in general are better as a result. I'll also point out the third paper reflects the progress we're making toward another objective in the OAR strategic plan, and that is to make forecasts better. Obviously, doing that relies not on the modeling alone, but also the observations that go into assessing the skill of those observations. So thank you all very much. Congratulations to all of the presenters and the collaborators and co-authors on these three papers. With that, Camille, I'll turn it back to you.
Hi, thank you, Gary. Congratulations to all the winners of this prestigious award. At this time, we would like to open the floor to the audience for questions. Please add your questions to the question panel, and we will do our best to get through as many questions in the time remaining.
Hi, Camille. This is Katie from the library. And before there's the questions, I just wanted to thank everyone for hosting with the library. And we are very, very excited to be a platform for these scientific papers. I have been placing in the chat so everyone can see that all of these papers are in the NOAA institutional repository. This means that they are open and publicly available to anyone inside, outside of NOAA to view. And I wanted to highlight that and make sure that everyone knew that they could access these papers.
Thank you, Katie. We appreciate that.
I'm not seeing any questions in the question panel, Camille, but I would like to, since we do have about 4 minutes left in the time, I would like to turn it back to each of the speakers and ask them if there's one thing they would, one more thing they would like to say that they didn't get to say. So if we could start with our first speaker, Stephen.
One more thing to say. To reiterate what Gary said, perhaps, which means it's already been said, and that is the importance of observation for what NOAA does, and the room for, at NOAA, for scientists to be actively engaged in making and interpreting and understanding those observations. That's all. Thanks.
Thanks, Stephen. Richard?
Yes, I just want to say that this work would not have been possible without the cooperation of many people nationally and internationally, but particularly NOAA's Office of Global Observations and Monitoring, and in particular David Legler and Kathy Tedesco, who have worked both at the national level and the international level to make these combined measurements work together. We have also worked very closely with the NOAA Operations Office for collecting the data on the NOAA ships and with the National Science Foundation. And we have worked with the information centers to make sure that the data are of the very highest quality and accessible throughout all of NOAA and internationally. And really, this is a clear example of international collaborations. We've had 14 different nations working together to acquire these data and bring them together at the international level. And I'm very proud of the fact that we are continuing to do this to this day, and providing the highest quality measurements that are surface to bottom in the oceans, and finding that it's really important to continue to do so. Thank you.
Thanks, Richard. Ayumi?
Sure. Yeah, I think one thing I did not touch on during my speech is that this work greatly benefited from rich network of observations in the Great Lakes region. In wintertime, we are limited by observational data that can be used for model verification. Satellite data, visible sensors are not kind of limited by lots of cloud cover, which we see a lot in fall to winter time. But in the Great Lakes, there are a few offshore flux towers, that continue to measure atmospheric condition, surface meteorology, air temperature, wind, and these basic variables. And also, there's a Great Lakes evaporation network, which measures evaporation and heat flux offshore in the Great Lakes. That was a really strong data source that helped our model verification and to ensure the improvement of our model from the coupling technique. In general, winter observations are sort of a gap, but we've been seeing increasing interest in wintertime limnology, and we are seeing more observations in Great Lakes in wintertime, which is great, and I believe that will help advance future weather modeling in the Great Lakes region too.
Thanks, Ayumi. Thanks again to everyone for presenting and for all of our attendees for being here. I just want to remind everyone we did record this, so if you wanted to refer back to something that was said in one of the papers or just wanted to share with a colleague, the library will put this up on our YouTube channel, and I'm going to hand it over to Camille to close.
Congratulations once more to all the authors today. Thank you for joining us this afternoon. We'd also like to thank the NOAA Library for hosting this special event. This concludes the 2021 Outstanding Scientific Paper Recognition. Have a wonderful afternoon, everyone.